Okay, so we're going to look at electrostatics part 4. And so we're going to look at the electric field, electric potential, electric energy storage, things called capacitors. Okay, so the electric force gives us an electric field. So just as the gravitational force, we can think of it as a gravitational field, and a satellite will go in orbit around a planet, an electron goes in orbit kind of around a proton. Not exactly the same, but it's due to that electrical force or gravitational force. So the electric field is represented by arrows. So it's a vector quantity. So it has a magnitude and a direction. So how strong is the force? What direction is it pointing? Now the vectors are defined as the direction of force on a positive charge. So here we have a central charge, a charge in the center, which is negative. And if you think about putting a positive charge at any point, then it will be attracted to the negative charge, right? So anywhere you put a positive charge, it's going to be attracted to that negative charge. And so that's why the electric field for a negative charge is a series of inward pointing arrows. Okay, and you don't actually need the charges there. That's just a way of defining it. So we sort of call those positive charges test charges. Okay, so I can erase the actual charges and just leave the arrows. Okay, inward pointing, because that's where a positive charge would go. Now they have a strength at any point of force per unit charge. So force is in newtons, charge is in coulombs, and that would be the strength of an electric field. So E we've used for energy. Here I'm using it for electric field. Okay, we don't use this equation much, but it is available. I think you've got one homework problem that needs it. And also, there's the inverse square law, right? So Coulomb's law obeyed the inverse square law. That's the force. So, of course, the electric field is based on the inverse square law, too. So if an object is charge is twice as far away, remember, then it will have 1/4 as much force on it. So the electric field gets weaker as you go out. All right, so it'll be 1/4 as much, 1/9 as much, 1/16 as much as you keep going out, out, out. Okay, so we could represent that by a whole bunch of tiny little arrows, bigger ones close in and small ones when we're further out, right? So anyway, but instead of doing that, what they did was they just figured out a way to do it using one straight or one long arrow. And the strength of the field, instead of being represented by the size of the arrow, is represented by whether or not they are close together or far apart. So these arrows are closer together. The arrows out here are further apart. And so where they're bunched together, that's a strong field. Where they're further apart, that's a weak field. Okay, so we didn't need to draw all the millions of little tiny arrows along the way to get the general idea of how strong the field is. Now, what about a positive charged object? Well, it would have lines radiating away, right? Because any positive charges will be repelled away. So the lines radiate outwards. In B here, what we've got is a positive charge and a negative charge. So what happens is that you have a force from at any point, you would have a force from both the positive charge and the negative charge. So your test positive charge would be repelled away from your positive charge, but it will be attracted to the negative charge. So those two forces being added up give you that curved shape of the electric field. The last one here is a parallel plate capacitor. And it's just two metal plates. So parallel plate capacitor. Pretend that's a C. Okay, so what's going on there is that you can hook this up to a battery, for instance, with a positive and a negative end, and just hook it up with some wires, and you can charge up those plates. And then you can take away the battery, and the plates will remain charged up. So what's going on there is you can see that any positive charge that's in there is going to be repelled from the positive plate and attracted to the negative plate. So the lines are going straight across pretty much, except at the edges, where they've got a little bit of a curve to them. And they're straight across to the right. Now, of course, if you put in a negative charge there, negatives are going to be repelled from the negative plate and attracted to the positive plate. So they would go the opposite direction. So the electric field is defined in terms of the positive charge, but a negative charge will just go the opposite direction if it's in that field. And here are some little tiny pieces of fiber that are being affected by, they're set in some oil, and then these black spots are where there's some charges. And so the little fibers are lining up along the electric field line. So you can see how they match the electric fields we were talking about. So this must be like a positive and a negative. This one here must be like maybe two positively charged ones. You can see in the middle, the electrons aren't sure what to do. They just kind of, or the positive charges, the hairs, they don't know which direction to go. So they just kind of line up there straight. Over here, we've got a parallel plate capacitor set up. So again, a positive plate and a negative plate. And here we've got like a positive here and a negative circle here. And one of the cool things is look inside the circle. The fibers aren't lined up at all. Because inside a conductor, there's no outside electric force that can get in there. Okay, it gets canceled out. So inside the conductor, there's no repulsing or attracting to those metal plates. It's neutral inside. So there's no direction to the fibers. So the electric field is canceled inside, and that's called shielding. And so we'll talk about that more in a second. Actually, let's just jump here. So electric shielding is inside a conductive material, then objects are shielded. Okay, so we'll talk about that a little later, but it also relates to if you're inside your car and a power line falls across your car, don't try to jump out because then the power will get you. But if you're inside your car, then you're shielded inside your metal vehicle. The electricity goes around the frame of the car, but inside you'll be safe. So don't try to get out, wait for someone to turn off the electricity. Pointy edges tend to gather more electrons because they've got positive shown here. Positive charges or electrons because they're not repelled away from the edge by things beyond it. So there are no positives here to repel. So what happens is that they end up crowding into the corners. Okay, and the last thing in here is about the electric potential energy. So just as you can drag an object up so it's got gravitational potential energy. Then when you let it go or cut the string there, the energy changes to kinetic energy as it falls towards the Earth in the Earth's gravitational field. Same sort of thing will happen. Here we've got a negative charge, which is making a electric field around it. Pulling a charge away gives it potential energy. Letting the charge go gives it kinetic energy. All right, so you've given it energy by doing work, by pulling that charge away. That's called charge separation. And if you do work, pull with a force times a distance, then you can give it energy. Work is force times distance. Okay, so you give it a type of potential energy. And that energy can be positive or negative, because we were just talking about pulling charges away, but also you can push charges towards each other that don't want to be towards each other. So like a spring can be pulled out or pushed in. In this case, the positive charge here, by pushing it in, then when you release it, it's going to go to kinetic energy. So you're giving it potential energy by pushing it, forcing it closer to the sphere. Okay, so electric potential is defined as electric potential energy per charge. So PE divided by coulombs of charge. So Q for charge. So potential energy over charge. And so anyway, it's not the same potential. It's called electric potential. Not the same as potential energy, but it is related. It's how much energy there is for each coulomb of charge. All right, so electric potential is electric potential energy per charge, and electric potential is also what we know as voltage. And so since potential energy is in joules and charges in coulombs, then 1 volt is 1 joule per coulomb. And when you rub a balloon on your head, you can often transfer millions of electrons, and that could be as much as 5,000 volts that you have created. If you see an electrical discharge like a spark, it is 30,000 volts per centimeter. So in my little device over here, I was creating sparks of about a centimeter strong or long. So that means that I had about 30,000 volts of potential. This is what's a capacitor. You charge up the two sides and you create a certain amount of voltage. So if you charged it with a 9-volt battery, then that would be 9 volts. Anyway, so it can retain that voltage. And these are little capacitors, the kind you might find, in a inside a circuit board. Here's the hairy girl again. And here's how a Van de Graaff generator works. A Van de Graaff generator works by having electricity come in, and a little brush scrapes the electrons onto a rubber band, giant rubber band here. So this giant rubber band carries the electrons up into this metal sphere at the top. Right, so there's a big metal sphere. Here's the electric band that's carrying the electrons. And so the charge gets carried up. And the thing is, it can build up a very large charge. So millions, well, usually we have one at the college that's about 10 centimeters jump. So that would be 300,000 volts. Okay, so it can build up such a big charge because the electrons on the interior are shielded. They don't feel the influence of the electrons on the exterior because they're inside a metal sphere. So then the electrons get rubbed off onto the secondary comb and they go up to the top because they're being repelled away from the ones inside. They go up to the top and they pop out, and all of a sudden they realize there's a big crowd of electrons, but it's too late now. Now they're on the outside of the sphere, they're stuck. So anyway, so the electrons come up, they pop out, and you keep building up a big, huge number, millions and millions of electrons to play around with. Okay, so anyway, so yes, the electric field inside the sphere is always zero. Inside a metal conductive surface is shielded. Okay, anyway, that's the end of the chapter. All right, so that was electrostatics.